Hi, this is Sonia Doucette. In this video, I'll show you how to calculate the pH and the equilibrium concentrations for all species present for a solution of known molarity for a polyprotic acid. This problem is asking you to calculate the pH and equilibrium concentrations of all species present in a 0.20 molar carbonic acid solution at 25 degrees Celsius. The first thing you want to do in these problems is to identify the species present initially and their acid-base properties. In this case, the species present initially are carbonic acid and water. The acid-base properties are that carbonic acid is obviously an acid, and that water can act as both an acid or a base. The next thing to do is to determine the possible proton transfer reactions based on the acids and bases present initially, so that you can determine the principal reaction, which is going to be the reaction that heads the ice table. So the possible proton transfer reactions here are one, where carbonic acid transfers a proton to water, where water in this case acts as a base, to give you the hydronium ion, which is what results when water accepts a proton from carbonic acid, and bicarbonate, or HCO3, which is the conjugate base of carbonic acid. The Ka for this reaction is Ka1 is equal to 4.3 times 10 to the negative 7. And we have a Ka1 value here because there's also a Ka2 value. And this is something that's special to polyprotic acids, or acids that have more than one dissociable proton. So the Ka2 value will be for the case when bicarbonate, which is one of the products in this reaction, donates its other proton to water to give another conjugate base and another hydronium ion. But for now, we're just going to deal with Ka1. The other possible proton transfer reaction is where a water molecule transfers a proton to another water molecule to give a hydronium ion and a hydroxide ion, and this reaction has an equilibrium constant of 1.0 times 10 to the negative 14. So this is a special equilibrium constant for water, known as the ion product constant, that is known at 25 degrees Celsius, and we would look up the Ka1 value for carbonic acid in a table of acid dissociation constants. So we know then that this first reaction is the principal reaction, and this is the reaction that will head the ice table. So now let's draw the ice table. We have carbonic acid plus water going to hydronium ions plus the conjugate base of carbonic acid, which is bicarbonate. The rows in this table are going to be the initial concentrations for all species, the change those concentrations undergo to reach equilibrium, and finally the equilibrium concentrations of all of those species present. You're given in the problem that the initial concentration of carbonic acid is 0.20. The initial hydronium concentration is approximately 0, because there's always a little bit present, but not much until carbonic acid actually transfers some protons to water. And we don't have any of the conjugate base present initially. The change in concentrations will designate as minus X for carbonic acid, so that when we lose 1 mole of carbonic acid, according to the reaction stoichiometry here, we gain 1 mole of hydronium ion and 1 mole of bicarbonate. Therefore, when we lose minus X of carbonic acid, we'll gain plus X for both the hydronium ion and the bicarbonate ion. So writing the equilibrium concentrations for carbonic acid, we have 0.20 minus X, and for hydronium ion and bicarbonate we have X. Now you can use the Ka1 value to solve for x. So first, writing the equilibrium equation, which will be Ka1 is equal to the concentration of hydronium ion times the concentration of bicarbonate divided by the concentration of carbonic acid. You know that the Ka1 value is 4.3 times 10 to the negative 7 because you've looked this up in a table, and substituting in for the concentrations of all the species in terms of x, or their equilibrium concentrations in the table, we have x multiplied by x divided by 0.20 minus x. So as always, it's nice to try to get rid of the x in the denominator because that will make solving for x much easier, and we won't have to use the quadratic equation if we can get rid of that x. So the next thing we do is to make an assumption. We assume that 0.20 minus x is approximately equal to 0.20. So what we're saying here is that that x value is so small that subtracting it from 0.20, or the initial concentration of carbonic acid, will not make a difference, such that we'll still be left with 0.20. If that's the case, we can just leave x out because it's so small. So if we're going to make that assumption, we should test it. So what we're going to do is rewrite this equation making that assumption. And what we get here is 4.3 times 10 to the negative 7 is equal to x squared divided by 0.20. Multiply both sides by 0.20, you're left with x squared is equal to 8.6 times 10 to the negative 8, and then take the square root of that number and you'll get 2.9326 times 10 to the negative 4. So we test that assumption by subtracting that x value from 0.20, and when you do that, you'll find you have 0.997. For this problem, we'll be rounding things to two significant figures. So when you round this number to two significant figures, you still have 0.20. So in this case, it's okay to make the assumption that x is very small. So now that you've done that, you've essentially solved for x. Here is your x value. And now you can say that the concentration of hydronium ions and also the concentration of bicarbonate, and this is according to what you've designated your equilibrium concentrations as for both of these species in the ice table, they are both equal to x. And if you round this x value to the correct number of significant figures, you find that you have 2.9 times 10 to the negative 4 molar for these two concentrations. You already know from when you tested the assumption that the concentration of carbonic acid is equal to 0.20, because in the ice table you've designated this concentration as 0.20 minus x, and you know that when you subtract x from 0.20 and round it to the correct number of significant figures, you still have 0.20 molar. So there is the value for that concentration. The next thing you want to do, because these aren't the only species that will be present at equilibrium, you also have the second dissociation step. And this step is where that the bicarbonate donates a proton to water to give you more hydronium ion plus carbonate, which is the conjugate base of bicarbonate. And this has a Ka2 expression. So the Ka2 expression will be the concentration of hydronium ion multiplied by the carbonate ion concentration divided by the bicarbonate ion concentration. So products over reactants as always. And what you can do here is solve for the carbonate ion concentration because you know Ka2. You can look that up in a table, and it turns out that it is 5.6 times 10 to the negative 11. You've just solved for the hydronium ion concentration, and you've also just solved for the bicarbonate ion concentration. So what you can do here is say that Ka is equal to 5.6 times 10 to the negative 11. Again, that's something you would look up. You know that your hydronium ion concentration is 2.9326 times 10 to the negative 4. You've already solved for that, and again, I'm not rounding to the correct number of significant figures quite yet because I don't want to make rounding errors during my calculation. And you're solving for the carbonate ion concentration, and then you also know that your bicarbonate ion concentration is also equal to 2.9326 times 10 to the negative 4. And in this case, it's pretty easy because these two values just cancel each other out, and you know straight away that the carbonate ion concentration is equal to 5.6 times 10 to the negative 11th molar. So you've solved for that concentration. One of the last things you need to do is solve for the hydroxide ion concentration. So you do that by using the known relationship that Kw is equal to hydronium ion concentration multiplied by the hydroxide ion concentration. Rearranging that relationship tells you that the hydroxide ion concentration is equal to Kw divided by the hydronium ion concentration. Substituting in the values, you have 1.0 times 10 to the negative 14th divided by 2.9326 times 10 to the negative 4. And what you'll get for your hydronium ion concentration rounded to the correct number of significant figures is 3.4 times 10 to the 11. The last thing you need to do here is find the pH. And by now this is easy. We know that pH is equal to the negative log of the hydronium ion concentration, which is equal to the negative log of 2.9326 times 10 to the negative 4. And when you do the math there, you find that pH is equal to 3.53. Once you've found that and the concentration of all of the other species present, you're done.